Introduction to the Cosmology module. So, just a second, sorry. Yeah, sorry. So, yeah, I'm Shruti Pikle, and today we'll be giving you an introduction to the Cosmology module. And so, every one of you might have dreamt of, sitting on a lawn under the night sky, looking at the stars, right? Everyone has that dream, and uh, you may also have wondered that how did how was the universe born? Like, what is its fate? What are its components? So all those questions are answered by one subject, that is cosmology. So cosmology, what is cosmology? Cosmology is a study of the universe, its components, processes, and the governing physics. Cosmology tells us how everything around us came into being as it is today. And in this module, we'll cover a very small part of the vast field of cosmology. And in this presentation, we'll give you an introduction, or rather an overview to the module. So the topics that we'll cover in this module are as follows. Introduction, the cosmological principles, scaling, scale factor, what is a metric, Hubble's law, eras of the universe, cosmic microwave background radiation, galaxy rotation curves, etc. So, and the topics we'll cover in this presentation are as follows. The cosmology principle, Hubble's law, redshift, Newtonian cosmology, and dark matter. Just a minute, sorry. Hello. Right, sorry. Yeah, so these are the topics that we'll cover in this presentation. And the first three topics will be covered by me, Shruti Pikle. The fourth topic is the Newtonian cosmology will be covered by Yashasvi Taiwade. And the last topic, the dark matter, will be covered by Dishika Naval. And the last topic is probably the most interesting topic of today for most of you. So yeah, let's continue with the cosmology principle. So what does this principle state? One second. Yeah. So the cosmological principle states that on a large scale, that is the scale of superclusters, universe is both homogeneous and isotopic. But what is homogeneous and what is isotopic? So homogeneous basically means that the universe has no special place. That is, wherever you go in the universe, at whichever point, the universe looks same at every point, will look same to you, right? And what is isotropy? It means that the universe has no special direction. So wherever you go in the universe, when whichever direction you look, the universe is going to look the same, right? To give uh, an example of homogeneity is if you consider a cylinder and if you imagine yourself standing on the curved surface area. So any point on the curved surface is same, right? So that is homogeneity. And isotropy, let's say you're standing in a dense forest, you have nothing to guide you. There's no defined route, or there's no map or anything. So in whichever direction you look, the forest is going to look same to you. That is why people tend to get lost, right? So yeah, that is isotropy. By the way, did you guys know that the universe is continuously expanding? Well, yes, and this expansion has started right from the day universe was born with the Big Bang theory and all, and it is continuing till today. And this timeline the from when the universe was born until the present day, the time has been divided into three main eras. So the eras of the universe are radiation-dominated era, which lasted in the initial 47,000 years, the matter-dominated era, which lasted from 47,000 years to 9.8 billion years, and the dark energy-dominated era that lasted from 9.8 billion years to the present day. So the radiation-dominated era was basically an era where um, the uh, the universe was dominated by photons and neutrinos that are basically radiations. In the matter dominated era, the universe was more dominated by the matter, as the name suggests, and more than the radiation. So the first protons, neutrons, electrons were all born in this era, which combined to form the atoms, which in return combined to form the molecules. Right? So the first galaxies and planets and solar systems and all that was seen in this era. So our galaxy was also born in this era, right? So the last era of the universe is the dark energy dominated era, which is probably the last era of the universe, and it is, as the name suggests, dominated by the dark energy. So this dark energy is slowly pulling the universe away apart, and this rate of expansion of the universe has increased with the dark energy dominated era than it was before. So fun fact, the end of the universe, the fate of the universe is there are three theories for the fate of the universe. The first is the big rip, the second is the big crunch, and the third is the big freeze. I'll give you a gist of what that is. The big rip is basically the universe is expanding, so it's continuously expanding, expanding, and then at one point, the dark energy dominates so much that it tears the universe apart. It rips the galaxies, black holes, stars, planets, everything. And the Earth, obviously, along with the humanity, might you know might decay into radiation, or the universe will just tear apart, and thus the it will lead to the universe being finally in a state of um, multiple single and disconnected particles. And the second, yeah, sorry, the second theory is the Big Crunch. So Big Crunch is just the opposite of the Big Bang theory. So basically, with time, eventually there'll be a time where gravity will dominate more than the dark energy. So the universe will start contracting again, will shrink, and it will shrink back to singularity. The galaxies and planets all will collide with each other and collapse into itself, right? And the third one is the big freeze. So big freeze is basically the movements of particle will cease, the black holes will evaporate, and the uh, expansion will be so much that the density of gas will be so less that no new stars can be formed, and thus the time will be an infinite void. So nothing is happening in the universe, and thus it appears like it's frozen. So it's the big freeze. It's also called the heat death, by the way. So yeah, so coming back to expansion. Uh, so expansion, what rate is the universe expanding? Can we measure it? So yeah, we can measure it, and that equation is given by the Hubble's law. So the Hubble's law states that galaxies are moving away from the Earth at speeds proportional to the distance. The equation is given by the as shown below, that is v equals hd, where v is the recessional velocity of the object from the with respect to the observer, which is given in kilometers per second. H is the Hubble constant, which is equal to 70 kilometers per second per MPC, and d is the distance of the object from the observer, again given in MPC. Here MPC is megaparsecs. So this Hubble's law will be explained in detail in the further slides by Yashasvi. So yeah, coming back to expansion. Uh, since the universe is expanding, it must have some effects, right? Some visible effects that we can notice. So one of such effects is the redshift. Yeah. So what is redshift? So the wavelength of light is stretched, so the light is seen as shifted towards the red part of the spectrum. So what does that mean? Let me explain. So we know the Doppler effect, right? We have learned about it. So as the object moves away from the observer, the frequency appears as decreased, and as the object moves towards the observer, the frequency appears as increased, right? So here we are talking about expansion. So the object is moving away from the observer, so the frequency is appearing as decreased, and thus the wavelength is appearing as increased. So the light appears stretched, and thus the light is seen as shifted towards the red part of the spectrum, right? So this is the Doppler redshift. But nowadays, better explanation is given for the redshift, and that is the cosmological redshift. So what is that? So in the Doppler redshift, it was explained by the objects moving away from the observer, that the object was moving, right? But here in the cosmological redshift, the object and observer are not really moving with respect to each other, but the universe itself is expanding, and that is why the distance between them is changed. So let me explain this with an example again. So let us take an example of an unbaked raisin bread. Okay, so let us consider two raisins in the dough, and they are at some distance apart, right? And they are at rest with respect to each other and with respect to the dough around it. Okay, so now we bake the bread, but now is the distance between the two raisins same? No, it has obviously increased, right? But so it appears as if the raisins have moved, but have they actually? No. The position of the raisins with respect to the dough around it is still the same, right? So the raisins have not moved with respect to the dough around it. But then why has the distance changed between them? It is because the dough has expanded, right? It's not because the raisins are moving away from each other. So the same logic is applied here. The objects in the universe are not really expanding, moving away from each other, but the universe itself is expanding, and that is why the distance between them is changing. Okay, so let me show you an animation here of the redshift, which might help you understand it better. Just a second. Sorry. So as seen, the universe itself is expanding, and thus the light is stretched and the wavelength is increased, and thus the light appears as shifted towards the red part of the spectrum. So the further presentation will be continued by Yashasvi, who will explain Newtonian cosmology to you.
Thank you, Shruti, for this wonderful walkthrough. So, next slide, please. Okay, so now we are going to get a bit mathematic. So we will talk about Newtonian cosmology. But what is Newtonian cosmology exactly? So Newtonian cosmology is a mathematical representation with some equations to help us demonstrate how the universe changes over time. So, but before explaining Newtonian cosmology, we must first introduce scale factor concept. So, scale factor, also denoted by AT, tells us whether the space is expanding or contracting with time. So, using the scale factor, we can determine the distance between 2 points in the universe as follows. We can write it as R proper equals AT into R co moving. So, R co-moving here is the distance between any two points in the universe at the present time, while R proper is the distance between two points in the universe in rest frame. Next slide, please. Next slide. I'm so sorry, are the slides not visible to me or is it for everyone? Oh, okay, it
Hello.
is visible now. Yeah, yeah, it is visible now. So, continuing. So, we already saw Hubble's law, but now we will actually derive the Hubble's law. So, Hubble's law basically tells us about the velocity of expansion of the universe, just as Edwin Hubble told us. One second, guys. I think the laptop is not responding. So, one sec, we will figure out.
Hello, is my slide visible?
No, it's not visible. We are really sorry for the inconvenience, guys. So we'll continue now. So Hubble's law can be derived as follows. We write the velocity as a derivative of distance with respect to time, which can be written as dr proper by dt. Now we will split the term. We get dat ri by dt. Oh, okay. We have written okay dat ri by dt, which can be further split into r dA by dt and a dri by dt. So this is done using the scale factor relation, and ri over here represents the arc moving term. So the dri by dt, it is quite low, and so thus we can write dA by dt as a dash, and we get the follows. V is equal to a dash by a multiplied by r proper. We have ignored that dri by dt term as it is quite low. Now the term a dash by a is called the Hubble's parameter, and it is roughly 70 kilometer per second per megaparsec. This value is not a constant. It changes with time, as we already saw that at itself, the scale factor itself changes with time. So finally, the Hubble's law can now be written as V is equal to h, the Hubble's parameter, into r proper. So now we will start with the derivations. So first will consider the distance between any two points as a radius and create a sphere around it. For example, in the figure given below, we can see that O is considered as the center and the distances OA, OB or OC are considered as the radius. So we have created a sphere around it, and OA or the distance of O with any other points is considered as the radius. All of the points are on the surface. So now we will just consider a few things like capital R as the radius of the sphere, A as the scale constant, X as radius at the present time. So from this, we get the scale factor relation as capital R equals AX. Then M equals as mass of the points A, B, C, or D. All of them are equimass. Capital M as the mass inside sphere, and it is a point mass at O. So now this mass can be written in the terms of density as density by multiplied by volume, and substituting we get the following term. Next, capital V represents the volume of the sphere, rho the density, r dash the velocity, and r double dash the acceleration. So the force acting on any of these points A, B, C, or D will be the gravitational attraction from the matter internal to the sphere, which is the point mass at O. So this force is given by F is equals minus G small m capital M by R square. Capital G over here, the gravitational constant, a basic gravitational force. So now this force can be written in the terms of mass into acceleration as m multiplied by r double dash over here representing minus g capital M upon r square. So finally, a relation between r double dash by r is written as follows. Now this mass can be substituted with density times volume, which we saw earlier. So now r double dash by r can be written in terms of density as minus 4 by 3 by capital G rho. So from the law of conservation of energy, we can write the above in the terms of total energy equal to kinetic energy plus potential energy represented by U, T, and V respectively. So the relation U is equals T plus V can be written as follows: half m r dash square minus G capital M upon R, which which on substituting capital M with density times volume can be written as follows. Now, as we earlier saw, this capital R in terms of the scale factor, it can be written as A times X. So substituting R as AX, we get finally this term for total energy, which is half m a dash square x square minus 4 pi by 3 capital G rho a square x square m. So now the earlier equation for total energy can be arranged into Friedman equation. So now what is Friedman equation? So Friedman equation is a set of equations which that describes how the expansion rate of the universe changes over time. So now we can write the above in the term of a dash by a square equals the following term. Now kc square over here represents minus 2u upon mx square. This is just rearranging it all and you will get the term. Now k is something new over here. So k is nothing but just a constant and it is unchanging with space or time. And the value of k just determines the form of this evolution. From the previous slides, we saw that a dash by a represents the Hubble's parameter capital H. So now substituting this with the previous equation, we get capital H square is equals 8 pi g by 3 times density minus kc square upon a square. So from the above, we can determine a critical density today. So, but what is a critical density? Critical density is a form when we achieve equilibrium, when the universe is neither expanding nor contracting. So this density is given by 3 h naught square upon 8 pi g, and h naught over here determining Hubble's parameter as present time, as Hubble's parameter changes with time. So from here on, Dishika will be continuing the presentation. Over to you.
Thank you, Yashasvi. Now I'll give you a brief about dark matter. I'll start with a little history. In early times, one of the astronomers was observing the motion of stars in the neighborhood galaxy, and he noticed a strange behavior. He observed that the velocity of the stars was way more than the expected was way more the velocity of the stars had way too much velocity, way more than expected by the galaxy's gravitational force. He observed that the mass of the galaxy was 3 times more than the estimated amount, and all of this mass was not emitting light. After some years, a- an astronomer invented a term known as galaxy rotation curves. So, what are galaxy rotation curves? Galaxy rotation curves are the plot of orbital velocities of visible stars in the galaxy and the distance from the galaxy's center. To understand it thoroughly, divide your galaxy into two parts, a more dense region and the other a less dense region. For the more dense region, assuming circular orbits and the average density of the stars to be rho, your mass will be density into volume, that is, rho into 4 by r cube by 3. Now, when you equate the centripetal force to the gravitational force, it's a very basic math. You'll get the relation between velocity and distance as v proportional to r. Similarly, for the less dense region, as it is far out from the center, it is essentially a point mass. So it implies velocity is directly proportional to 1 upon root r. So, what does we draw from these theoretical calculations? We conclude that the graph of velocity and distance should be like the first one, like this, where the velocity is increasing initially with the distance, and after a certain point, it starts decreasing. But the reality was completely different. After a certain point, the velocity was constant. Here is an animation showing Here is an animation showing two galaxies. The first galaxy is the galaxy whose mass is concentrated on the center, and the second galaxy is a galaxy who has its mass evenly distributed as we get further away from the center. To keep the speed constant, there need to be a mass distributed throughout the system and not just at the center. But the galaxy is brightest at the center, as in the first one. So scientists thought that maybe all the mass doesn't give off the light. Another analogy could be that normally the velocity of stars along the periphery of the galaxy should be lower as compared to the stars at the center. But the actual data told us a complete different story. In observations, we found out that the orbital velocity remained almost constant even when we move further away from the center. That is, it's that the it implies that the galaxy shouldn't be stable. They should be sort of flying apart, but they are not. So there must be some sort of force which is keeping the mass inwards. It implies that there must be some gravity or some mass which we are unable to see. So these all ideas leads us to the idea of the dark matter. What is dark matter? Dark matter is a material which is not luminous, has gravitational effects, but doesn't interact with electromagnetic forces. It is not known to interact with any ordinary matter and radiation except gravity. We don't know yet what makes up the dark matter. The most prevalent explanation one could get is that dark matter is made up of some undiscovered subatomic particles such as axions. Here there is an Milky Way halo structure. The outer halo, the outer halo is representing the dark matter. Going ahead to the dark energy. So what is dark energy? Dark energy is the mysterious something that is causing the universe to expand at an accelerated rate. It is the fundamental ever present background energy in space known as vacuum energy, which could be equal to the cosmological constant. It is described by some as having the effect of negative pressure that is pushing the space outward. But we don't know yet that what makes up the dark energy as and what dark energy has the effect of any type of force at all. Going ahead, here there is an energy distribution of the universe. 69% of the universe is made up of the dark energy, and 26% of the universe is made up of dark matter, and only 5% of the universe is made up of normal matter. Isn't it surprising? So thank you to you all. We are at the end of our presentation. To dive deeper into these topics, I would encourage you to explore our comprehensive module on cosmology. Thank you. We'll be happy to answer any questions you may have.
So, anyone has any doubts? You guys can post the doubts either on, you can either post it in the chat section or you can also unmute yourself.